Okay, so can you hear me?
Yes.
Okay, so good afternoon, everyone. We are going to continue today with programming with Python for data science. As you can see, I've also provided you with a link to a mega repository through which you can download today's materials. So today we're going to start delving into machine learning algorithms. More specifically, we are going to start with clustering, and tomorrow we are going to move on with classification. So let me share my screen real quick. I'm guessing that you can now see my screen as well, right?
Yes.
Okay, great.
I see it.
Okay, great. So just as a quick reminder of what we've seen so far in terms of, oh, sorry, was there any question or something that someone, oh, okay. So just as a reminder, yesterday we actually delved into an introductory course when it comes to pre-processing and exploratory data analysis. We used Iris, which is a benchmark data set. The day before yesterday, we basically went into the basics of Python and how to set up a VNV and all the necessary libraries. So today, before we start, we basically go on with clustering and what machine learning is and what the main types of machine learning are. I'm going to remind you how we can actually create a VNV, how we can turn it on, how we can install libraries. And the reason behind this is the more we actually get used to the commands and the more we come in contact with them and use them, the more familiar they're going to be for us um, later on down the line when we actually want to use them for a real problem or a real project that we might run into. So um, after we've set up Python, the first thing that you got to do in order to create your VNV, I'm just going to remind you the commands, is write python /m VNV VNV. This is how you create it. Once it's created, you're going to have to activate it. So you do this through this command in Windows. You've seen that I'm using a dot here because this is the name that I also gave to my VNV. So if you had named it simply as venv without it, you should actually give it as such. So if I do this, now you can see that I'm inside my VNV. And the other thing that we've also said is that in order to be able to download and install every single requirement that I need for my project is to basically create a txt file, which is going to be called requirements with these particular with these libraries, and then basically use this command in order to be able to install everything correctly. So is there any question, any problem? I'm asking because after yesterday's course, there were some questions about this. Some issues actually arose when it comes to running these commands. So if there's anything you want to ask, feel free to do so. Let me also check the chat. Okay, so I'm guessing so far so good with the whole procedure of VNVs and how to set them up. Okay, so no news means good news, I guess, in our case. So let's start again by using our Jupyter Notebook. Again, you can use any other kind of editor you might have. So if you have Visual Studio Code, for example, you can use that. If you have Spider, again, feel free to do so. We don't really have any specific requirements in terms of the tools that you can use. So okay, let me restart the kernel. Oh, another trick when it comes to notebooks is that if you actually run a specific experiment and then you want to basically erase the variables that you have stored in memory and also the results so that you can actually rerun the experiment from scratch, you can go there in kernel and basically have this, like restart kernel and clear outputs of all cells. And that way, the memory will be cleared. And at the same time, the outputs, as you can see, have also been cleared. Okay, so before we start with what machine learning is and what clustering and classification actually mean for us, because we also need to make clear this kind of differentiation, we're going to also be reminded of the basic strategy that we follow when we write code in Python, especially with notebooks. So the first thing that we need to do is import every single necessary library that is required for the analysis that we want to do. The second thing that needs to be done, as you can see, it runs a bit late because some packages are a bit, heavier compared to others. Okay, so the next thing that we need to do is initialize functions that are homemade. So this is a function that I've created in order to be able to plot the data that I'm going to use, as you will see later on. And then, of course, what we need to do is basically read our data set and maybe pre-process it a bit, like, for example, normalize it. As you can see here, for starters, we're going to continue with Iris, just because it's a very good benchmark. And later on, we're also going to see a bit of a more complex example so that we can differentiate between different clustering algorithms. So having said that, you can see that we have our data set again here in the form of a data frame. What you will notice here is that we do not have the species column. We are going to explain why that is in a bit. And then, of course, we can also keep it and also create our PCA. So with all that being said, let's start with what machine learning actually is and why we actually really like it. So machine learning essentially, let me also put up a picture here so that we can get a better understanding. So machine learning essentially is a subfield of artificial intelligence through which we basically get data, and I'm talking about large amounts of data, and we feed it into certain algorithms so that they can actually mimic the way we make decisions. And by decisions, I mean predictions, the way we would actually try to infer certain concepts, whether that is predicting certain classes of things, whether it is, making predictions or assumptions for numbers, or whether it is grouping, many different samples or objects into different kinds of groups. The reason why we say that it's a different thing or a subfield of AI is because AI is more of an umbrella term. And this basically means that AI is essentially the basis that helps us understand how we can mimic, human cognitive thought and decision making. However, it includes many different other algorithms and fields. It can actually, AI can include some things like rule-based systems. It can include logic, etc. So machine learning is basically a specialization of AI, if you will, that focuses mostly on large, big data sets. The reason why it has become extremely prevalent in recent years, of course, is not only because of the fact that we have huge amounts of data, like thousands of different samples, as well as features for many different fields of expertise, but also because of the fact that we have the required computing power that is needed to be able to not only create algorithms, but also train and subsequently evaluate them on such data. Okay, and then of course you can see here that we also have deep learning, which is a subfield of ML, so the subfield of the subfield itself. So deep learning, so that you can have a better understanding, is essentially machine learning that concerns artificial neural networks. So these are essentially a specific type of model, a specific type of architecture that tries to model, the human brain. So they're very complex. They're nonlinear in nature. We might see some of them during the end of this course, like in the 10th of December or the 17th. I don't know yet. But they are very, very prevalent because they can actually handle extremely complex and large amount of data very efficiently in many different fields of expertise. Oh, is there?
I have mute them all. I have mute them all, but I had to mute you as well, so you can unmute yourself now.
Okay, so can you hear me now?
Yes.
Okay, great. Okay, so this is the basic definition of what machine learning is. So what are the categories of machine learning? Let's delve into that for a little bit. So you see here that there are basically two main prevalent categories of machine learning, like supervised and unsupervised. There is also a third one, which is called reinforcement learning, but we're not really going to delve into that. I'm just going to mention a few things about it later on. So just to make things a bit clear, whenever you listen to things about supervised learning, I want you to think of classification and regression tasks. Whereas when we actually mention unsupervised learning, I want you to think of clustering. So what is actually the real difference between the two, right? So that we can actually get a better understanding of why we might want to use one over the other, or maybe a combination of both of them in some cases. So take the iris dataset, for example, right? It has 150 samples. It has 4 numerical columns or features, but it also has a categorical feature at the end, which is the species of each flower. Now, the species of each flower is essentially a ground truth that has been given to us by the person that actually annotated every single one of these 150 flowers, of course. So when we talk about supervised learning, for example, like in the context of classification, what we do is that we give a model. The model is synonymous with the algorithm that we use. So whenever I mention model, think of it as the algorithm that we have. So we provide our algorithm with two things. We provide it with the input numerical features that we have for each sample. So we provide it with this matrix right there. And we also provide it with the ground truth that we have for our data. Essentially, it's to make things a bit simpler, perhaps, it's basically like trying to teach a small child what they're looking at. Like imagine having a small child, you give them certain fruit, and you tell them that, you know what, this fruit that looks like a sphere, but it's not, and it's smooth and it's red and whatnot, this is an apple. The other type of fruit that you have available is orange and spherical, so this is called an orange, and so on and so forth. So the end result of this process is a trained model or a trained algorithm, which is able to make predictions in regards to the ground truth that we have on previously unseen samples. It's basically, again, like taking a kid and basically telling them that, you know what, I've taught you what different types of fruit exist. So I'm going to show you a new object. I'm going to show you a new fruit that you've never seen before. And you have to make a prediction of what it is based off of the attributes of that fruit, like the texture or the color or even the shape of it. So why do we say that there are two different supervised learning tasks like classification and regression? Well, it comes down to the target variable that is used in each of these tasks. So in classification models, the target variable is categorical, which means that we basically have a certain class. Like, for example, the fact that we're talking about different fruit in the kind of silly example that I'm mentioning right now. The tag could be pretty much anything else. It could be the species of flowers, as we've seen in iris, for example. It could be in a biomedical context, whether a person is suffering from a specific type of disease or not. In a more general context, it could be whether the email that I've received in my inbox is either spam or not, and so on and so forth. So this is classification. We have a categorical output variable or a target. On the other hand, we have regression. So regression means that we basically have a numerical continuous variable. So we are basically training models so that they can actually predict specific numbers. And this is very useful. For example, in economics, we might want to basically predict the price of a specific stock at the stock exchange, for instance. We might want to predict the price point of a specific house, depending on where it's located or how big it is and whatnot, so on and so forth. So on the other hand, we have unsupervised learning. So in the context of unsupervised learning, what we actually want to do is basically get some input samples, ignore the ground truth completely, even if it exists or not, and basically try to group these samples that you see there, for example, these fruit, into specific distinct categories. It doesn't matter how these categories or groups or clusters are actually named. They could be named like group 1, 2, 3, A, B, C, whatever. But what we actually want to achieve through this process as a final result is a specific number of distinct groups where the samples that belong to the same group are actually very close to each other. And this, of course, always happens in accordance to their attributes, their features. And we also want that samples that belong in different groups or clusters to be as far away from each other as possible so that we can actually have very, distinct teams or clusters of objects. The equivalent, again, in the silly example that I've mentioned before, is like taking again a kid, you give them a bunch of fruit, you do not tell them what these fruit are, no matter whether bananas, apples, or what have you, and you tell them that based off of the attributes that they have, like their texture, their color, what have you, I want you to create specific, groups of them, which are going to be distinct from each other. And this is the result that they're going to give you if everything goes according to plan in the end. So, um, given all of this, is there any question as to what are the main differences between supervised learning or unsupervised learning? I think that this is actually a very important part of this series because in a lot of cases there might be a bit of confusion as to clustering and classification and regression. So it's very important to actually be crystal clear about these kinds of concepts. So are there, any questions when it comes to these particular concepts and whatnot? Oh, so I see. Oh, okay. So no questions in the chat. Are there any questions you would like to ask? You can always, of course, open your microphone. Okay, so let me reiterate. Is everything understandable up until this point as to what we actually mean by supervised and unsupervised learning?
Yes.
Okay, great.
Yes.
Okay, so the question might be, when do we actually use unsupervised learning, right? So why would we actually use clustering, this kind of approach, when we can actually go to classification, right? Since we might have a certain type of ground truth. Well, the answer to that is that unfortunately, in a lot of cases, you might not really have a ground truth. You might not really have a specific categorical or numerical value that you need to, differentiate between different groups or things that you have between different categories. So in these situations where your final outcome is pretty much unknown, it's better to go with clustering rather than trying to create, a ground truth from scratch, which might also be wrong. The second reason why we might want to use unsupervised learning is in cases where we actually have multiple ground truths. For example, in some kind of problem, we might have 3 or 4 potential target variables, like 3 or 4 categorical variables that might serve as our tag. And we might not be 100% sure as to which one we should actually use. So in order to get a better understanding of the tendencies within our data, and to also understand which of these variables would actually help differentiate between samples, what you could do is start with clustering, with unsupervised learning, without, of course, without using the set target variables, without taking them into account. And then after you've obtained a certain number of groups, a certain number of clusters, you can actually see how these clusters actually align and differentiate in relation to the target variables that are available. So you can actually basically make a combination of these two strategies in situations where things are not really clear on how to, approach a certain problem. Now, are these the only two types of machine learning models, the only two disciplines of machine learning? The answer to that is no. There is also a third one. There is also reinforcement learning, which again, we're not going to occupy ourselves with this. But just to put it into a bit of a context, reinforcement learning is what is actually very prevalent when it comes to robotics in a lot of cases and things like self-driving cars. So if you actually watch videos of a car that actually evades certain obstacles and stops itself from crossing into such obstacles, it's because a certain reinforcement learning algorithm has been used to prevent this from happening. So, but this is basically just for, as I'm mentioning things so that you can have a good understanding of the differences between models. So having said that, we are going to check out different clustering algorithms. We're actually going to test 3 different clustering models, these being k-means, hierarchical clustering, and dbScan. We are going to describe each of them for a little tiny bit. And then we're also going to see some examples, starting with Iris, and then moving on to something a bit different. Okay, so the first algorithm that we have is k-means. So as you can see, I've also put a GIF there so that we can actually get a visual understanding of what's going on. So k-means is actually, I'd say, one of the oldest and more well-established clustering algorithms. So what it actually does, first of all, k-means has an input feature that you have to provide it with, which is called k. So the k in k-means indicates the number of clusters that you want the algorithm to create, right? So let's say, for example, to make things a bit more concrete and in accordance to this example that we see here, that we have that we basically have 4 clusters that we want to be created. So what happens is we provide k equals 5 to the algorithm, and then the algorithm itself, k-means, will create 5 random points for us, which are these big circles that you see. And these are actually called the centroids. These are the central points that serve as hubs within our data set. So the goal here is to be able to assign our samples, which are these little X, things right there, into specific clusters based off of which centroid is actually closest to each point. And in order to do this, we employ certain distance criterions. For example, Euclidean distance is a very popular one, or cosine similarity in some other cases. And what happens is that after we've assigned points to specific clusters, we then update our centroids. So what we actually do in order to update the centroids in like two-dimensional format, as you've seen here, if we only have 2 dimensions, we basically get the measurements of each sample. For example, let's make things a bit simpler. Let's say that out of the Iris dataset, I only have these 2 features right there. Or let's make it even simpler. Let's go to PCA. Okay, so forget the species for a bit. Let's ignore that, right? So I've got these 2 principal components. So when I'm using k-means in the context of our example, if we actually set it to 5 clusters, it's actually going to create 5 points that have random PC1 and PC2 values. And what will happen is that points will be, the samples will be assigned to each of these 5, large centroids or central hub points, which are basically the representatives of our 5 clusters, according to how close they are to each other. So each point will be assigned to the closest possible team or cluster, whatever you want to call it. So when we actually have every point set up to a specific team, we need to update our centroids, our central points, basically. So how do we do that? We are going to take every single one of the values for PC1 and PC2 for each point that belongs to a specific cluster, and we're going to find the mean or the average. So for example, what will happen in this case, I'm going back to the example, is that I'm going to take the average of all green points for PC1 and the average of all green points again for PC2, And the average, the values that I'm going to calculate are going to be my new PC1 and 2 for my centroid. So what I'm basically trying to do here is try to move the position of this centroid in this two-dimensional map within my data set so that I can actually check out whether anything is going to change. And by change, what we basically mean is whether a certain sample is going to be assigned to a different, cluster. Like, for example, as you can see here, when we move a bit further on, some samples that belong to this yellow cluster are later on assigned to this green cluster right there. So when does the algorithm actually stop working? When does it terminate? When we update our centroids, just as I've said, by using the average, and no new points are assigned to different clusters. So if we actually have a stable final representation of our data set where nothing really moves and budges away from one cluster to the other, then this is basically the final cluster representation of our data. And that way we basically have the final cluster map, which we can use to understand which samples belong into the same group or team. So in order to be able to check this, of course, with Iris, what we need to do is use, for example, k-means. In our case, you basically initialize it like this. And of course, later on, we basically execute the algorithm by using fit-predict. And then, of course, we can basically use the PCA dataset by also coloring samples by their corresponding clusters. So another thing that we've done in this PCA plot right there is that aside from coloring samples by their corresponding cluster, in accordance to k-means, of course, we've also kind of took advantage of the ground truth label that we had so that we can actually use different shapes so that we can understand whether the clustering actually took place. However, to make things 100% clear, this ground truth right there has not been used during clustering. As you can see, when we went on to cluster our data, we used the PC dataset without this part right there. We basically dropped it. So why do we actually do this? Why did we make use of these shapes again? So that we can have a 100% concrete understanding of the clustering that we did, that it actually mattered, that it's actually relative to what the real ground truth of our data is. So in some cases, clustering can also be used to confirm findings that we've seen, through dimensionality reduction or other similar techniques. So what do we actually see here? We basically see, once again, that we have a group which is called 1. So the second group of our data set basically includes all of Setosa's samples right there, right? So this is a very distinct group, and it basically aligns perfectly with what we've seen yesterday, where Setosas were actually being differentiated compared to the other two groups of samples. Okay, so this is the first thing that we see. So the other thing that we can also check out is that although there are some other two clusters, like cluster 0, the first one, and cluster 2, which is the third cluster of our data set, things are not really as clear as when we apply the same, concepts or conclusions to Setosas. And the reason why I say this is because both of these groups actually contain samples that belong to either versicolor or virginica flowers, or samples if you prefer, which means that although there are certain, distinct samples, for example, these ones that are up there that belong to cluster 2, they are actually considered to be, according to k-means, of course, different compared to the virginica flowers that are down here. So even though they belong into the same species, in the same kind of category, what we've seen through these plots right there, through this representation, is that the final result showcases that although they belong in the same category, they are not really all that close to each other in practical terms. And this is another insight that we can use in order to be able to find even the most subtle of differences between samples that belong in the same kind of category. And to put it all into a bit of a context, like an extension, for example, in a biomedical problem where we have patients and we clustered them into specific groups, yellow could actually indicate that these are cardiovascular patients, like they have a cardiovascular disease A, and these people have, again, cardiovascular disease B, but for some reason, these have more of a tendency to have severe effects due to the disease compared to these the ones right there. So what I'm trying to say here is that this particular differentiation between clusters can in some cases actually help us identify or highlight hidden patterns that the ground truth might not make all that clear or available to us, of course. So with that being said, um, again, are there any specific particular questions? So
Hi, I have a
okay,
question. I'm
yes, of
Adel
course.
from
I'm also
Hungary.
checking the chat for.
And sorry for this, but I didn't catch it that why have we exactly five clusters in our first example? Did
Mhm.
you choose it or did
Oh,
you choose
this
it
one you
by
mean?
Yes, exactly.
Oh, this is a visual example that I just found online to make things a bit more concrete. I didn't choose it. It's a different data set. Like it's basically just for showcase purposes. It's a
Uh,
different data set compared to what we have here, if that's the question.
yes, thank you. I understand it, but I was not sure that why have we started with exactly five clusters.
Oh,
So is this the five?
this
Is this number fixed by the system or?
oh, this particular one is arbitrary. It could have been any amount of clusters. Like this is a particular example where the people that created the GIF basically chose 5. It could have been 3. It could have been like 2.
Okay, okay, thank you very much.
Okay, so I'm also going to mention how we can choose, certain K for K-means, a bit later. So let me check a bit the other questions as well. So Ioannis also comments on the difference between supervised and unsupervised learning. And we also have Matei. So let me just read the question because the letters are a bit small in the chat. So bear with me on that. Yes, the answer to that is that you could still use k-means, but because of the fact that you would have, again, an imbalanced data set. So the question, to reiterate, is what would actually happen if we had an imbalanced data set? Is that correct? Is this, do I understand it correctly, Matei? Okay, so yeah, the answer to that is that you could be using k-means as well. You could definitely check out what's going on with it. You can experiment with it. But again, in some cases, when it comes to clustering, the fact that you have an imbalanced data set might have meant something completely different when it comes to, comparing between classification and clustering. So although imbalanced data sets might pose a problem for classification because we need to have equal representation so that our algorithms can make fair and accurate predictions, in clustering, these fewer samples, the minority group might have differentiated from the rest of our samples and might have created a very small group on its own. For example, if I actually used, let's say, for example, that we have a differentiation group right there, like these were in a fourth category called whatever, for instance. So if I actually saw through k-means that these samples right there that belong into a completely minority kind of category are grouped together in my plot, then this would be an indication that for some reason these samples are completely differentiating themselves from the rest of my data set. So this could be a further insight that this is a very, particular, very specific group, although they are rare, and rarity in such data sets is not always a welcome thing. It could also mean that they have a certain set of attributes that help them differentiate, at least in the context of clustering. And it could actually help us, gain a better of an insight as to how things are different which might not have been as clear in the first place, you know. And but that always depends on the data that you have and the kind of measurements that are included in the data set that you use. So I don't know if you have any further. I mean, is that clear? Do I? Okay. So the other question is, how do we actually use a specific value for k? For example, why did we use k equals 3 here in the context of Iris? Why didn't we use 4 or 5? So the number of k, so one of the things that that we have to make clear about machine learning is that in a lot of cases, it's more like cooking. So the reason why I say this is because our algorithms actually have a set of parameters that we can initialize them with. However, in a lot of cases, finding the optimal or combination of these parameters, like a value of k equals 3 along with something different, is more like a procedure that comes through trial and error. In other things, in a context where we didn't really have a ground truth, where we didn't really know what was going on within our data, we would probably, if not always, actually try many different values of k so that we can actually understand how groups are differentiating from each other. So we would start with k equals 2, for example. We would move forward with k equals 3 for, we can make all sorts of different experiments on this. However, the other thing that we could do is also employ an algorithm that is basically used for optimization. Algorithm optimization is also a choice. So what that means is that we can employ a certain criterion or a policy through which we are going to find the best possible pairs of our parameters that actually help us maximize a certain score. For example, an evaluation score for clustering, which would be a silhouette score, which we're going to check later on. But in most cases, what we would actually do, especially in the context where we don't know the ground truth of our data, is basically check. The simplest thing to do is try out many different values of k. The reason why we picked 3 clusters in particular, in our case here with Iris, is because we actually based that decision on the ground truth. So even though we didn't take the ground truth into account when it comes to making the prediction with k-means, we basically had this basically served as our basis for the number of clusters that we have, because we basically have a data set with 3 different species. If it was a different kind of data set, like something again where we didn't know what the ground truth is, we would have tried with many different values of k, or we would have used something like an algorithm optimization criterion, as I've mentioned. So I see. Oh, okay, great. Okay, so yeah, of course. Is there?
I have one question.
Yeah, of course.
The only part that I didn't understand is that every iteration the centroid change based on the distance, for example, and there are other methods.
So if there
Distance
is
of what, and like
So-
what are we processing? All the values with the distance of all the values, or distance between the like it's obviously centroid and the different values, but like every iteration we check the whole data.
Yes, this is the thing about these algorithms, because it's not like supervised learning where you have a training set or a testing set. But I'm getting ahead of myself. We're going to see what's this tomorrow. What you basically have here is your whole entire data set. So you start with specific central points, as you see, and I will say again that these central points, when we start using the algorithm, when it's initiated, where it's initialized basically, these starting points are random. So these large circles, when the algorithm starts working, have values, for example, PC values, like the ones that you see here, that are calculated at random. They basically use a pseudo random generator for numbers in order to do this in Python. So after these have been created, the criterion that we use in most cases in order to determine to which cluster each sample belongs to would be something like the Euclidean distance. This is actually the most common, the most established criterion when it comes to basically understanding which sample belongs to which particular cluster. And after we've done this initial attribution of different points to different clusters, of course, what we need to do is basically update our centroids. And the reason why we do this, the reason why we update our centroids, is in order to account for the initial randomness that we actually insert into our model. So we basically say that, you know what, okay, I'm starting with my centroids being random, but I want to see what will happen if I create a slightly newer centroid. Will anything change? Will new samples be assigned to my cluster? Will some of the samples that existed in my cluster to begin with, leave and be part of a different group, for instance? So the way we do this is basically take only the values of the sample points in order to calculate the new centroid. In other words, in order to update the centroid's coordinates, so to speak, because we have a two-dimensional plot here, you're actually going to use the values of your subsequent samples for each cluster, but you're not really going to use the values of the centroid. These are the ones that you want to update. So in each case, you are going to be using the average of your samples and those only. And of course, the algorithm terminates again when, even though you've made the final centroids, even though you've updated their coordinates, nothing really changes in terms of samples, which means that in each cluster, the same samples actually belong in the same clusters. Nothing has really moved on from one cluster to the other. So is it a bit clearer now?
Yes, it's clear. And if we go to the other plotting, can we go to the yeah here?
Oh, this one, yeah.
It means if we run a cluster with 3 centroids, like the k is equal to 3, is it true? I'm just guessing. Is it true we might get an error that one of these species will be in another cluster? So that is so if we come up, I cannot Setosa, versicolor, and virginica. So one of these virginicas and versicolor will be in the same cluster, only one element in our example. Is it true? Based on visualization and the one that you're pointing on, I guess, or I'm pointing on something.
Yes, absolutely. Yeah. It could mean that so this could actually mean one of two things in this case, right? So it could either mean that, for some reason our algorithm did not work as expected. It was not able to make distinct clusters or groups of samples. And in our case, distinct means that we would expect, at least, since we also have the ground truth, that each of the samples that belong to different species will form their own distinct clusters. Like, for example, we will have a cluster for Setosas, a separate cluster for versicolor, and a separate one for virginica, right? So it could be said, one of the things that we could be saying is this. The second thing we could be saying, however, is basically take an approach which will be a bit more independent from the ground truth. Like that, it's true that, for example, this particular sample right there belongs to virginica and this one belongs in versicolor. So yes, they do belong in different species. However, for whatever reason, my clustering, when I used k equals 3, actually says that they belong into the same group. So the fact that they belong into the same group could actually indicate that although they come from different species, their attributes, their features, the way they look, for example, is actually quite similar. they're actually very close to each other. And the same thing can be said, for example, for these Virginicas right there. You can see my cursor, right?
Yes, we do.
Okay, so the same case can be made for these Virginica flowers right there in comparison with these ones right at the top. So although these belong to the same species, essentially, we can see that they are pretty far apart from each other in this two-dimensional representation, and that they also belong into different groups. So even though they belong to the same category, in the end, it seems like these samples, these particular samples in our case, are not really as close as we would expect them to be. In Iris, of course, um, it could be argued that perhaps the classification that was made by the dataset's creator was not really correct, so they've made an error for this. Or but by extension, in other problems, in other contexts, it could actually indicate new insights that are not really known, through the ground truth that was provided to us by experts in certain fields of expertise. Hence why I also made reference to the biomedical example before, like with the disease and whatnot. So,
Yes. Yeah,
okay,
thank you. Thanks a lot.
okay, you're welcome. So let me check on the chat. Oh, we don't have any other questions. Okay, so let's move on to another algorithm, another clustering algorithm. So K-means is actually one of the most established algorithms out there. There have also been many different variations of it that essentially improve its performance. They make it a bit faster. They make it account for local neighborhoods, some of them at least. So there are many different variations that you could also try, for many different types of data. So moving forward, we go to hierarchical clustering. So and you can see basically this tree structure right there. So what's the difference between this and k-means? So this one actually tries hierarchical clustering, that is, tries to create a hierarchy of clusters. So it's basically like what we are trying to do when we try to group different species of organisms together, starting from like a common ancestor, right? So there are two different ways to approach it, as you can see here. One of them is agglomerative, and this is what we would also call as bottom up, because we go from the leaves of the tree all the way out the top to the root, or top down. So what does that mean for us? What does agglomerative hierarchical clustering actually mean? So the leaves that you see here at the bottom, you can see with my cursor, each of them actually represents a specific particular sample. So if we actually tried to visualize this for Iris dataset, it would actually be 150 of these leaves. So when we start with this algorithm, each sample constitutes its own unique, cluster or group. So what happens later on when we start using the algorithm is that individual samples that form said individual clusters, will start be grouped together into larger and larger groups according to a specific criterion. And again, pretty much like in the case of k-means, the criterion that we use is a distance metric, something like Euclidean distance, again, cosine similarity, or something similar to that, right? So at the end of this procedure, what we get is larger and larger groups or clusters of elements, right? And we end up having a supercluster that includes every other subcluster that has been created along the way. So this is called agglomerative hierarchical clustering. The opposite of this is divisive hierarchical clustering. So what happens is that we start out with a supergroup that includes every single one of our samples, and then based again off of a distance criterion, we try to separate between more distinct, more individual looking groups. And what we end up with is actually forming, a small cluster which only contains each of these samples individually. So why is that beneficial for us? Like agglomerative, for example, or divisive, depending on where you want to go, is because we can actually check what's going on when we start out the process, whether we're talking about going bottom up or top down in that case, and we can check the hierarchy of different clusters. So by having a dendrogram like this, we can understand which clusters are actually very, very close to each other. For example, if I want, and also, by the way, if I wanted to get, for example, 2 large clusters out of my data set, what would I actually do? I would actually run the algorithm, and then I would basically cut or prune the hierarchical tree that I get so that I can have this big cluster right there that includes the blue and green branches. So this one would be my cluster number 1, for instance. And the second cluster would be this one right there on the right, which includes all the yellow and red branches, as you can see. And then there's also an example of how agglomerative clustering works. So as you can see, depending on their distance, different samples are actually grouped together. And then the final result is a supergroup, which is indicated by this line right there. So for instance, if I wanted to have 3 clusters, like in the case of Iris, for example, I would stop right there in this particular part of the plot that basically passed. So I would have, for example, cluster 1 right there in green. I would have cluster 2, which would be it's a single point, P3. And then I would also have cluster 3 right there, which would have these red points like P4, P5, and P6. So it basically is very similar in terms of how it works to k-means, but because of the fact that we also have a hierarchy, it's a bit more interpretable in terms of what's close to each other and what's not. So it can be a very good basis, especially when it comes to fields like, biomedical problems, where we might want to see which samples are very close to each other, either in terms of evolution or in terms of a specific type of disease or what have you. So how do we actually run this particular algorithm? Well, it's pretty much the same as what you would have with k-means. So you basically initiate the algorithm itself, and then again you use fit predict. And once you run this, you can also plot PCA again, but this time you can basically use the clusters that have been assigned by hierarchical clustering. So we can create something like this. So what do we basically see here? So not a lot of things have actually changed, right? So there have been some changes, however. For example, some very minor subtle changes, which are attributed to the way this algorithm works or how it's actually based to work. So I'd say that the more characteristic differentiation between the two is that although we had all setosa samples be in the same category, in the same cluster using k-means, with hierarchical clustering, we now have this sample right there, which is said to belong, according to hierarchical clustering, of course, to cluster number 2, or the third cluster that has been created. Now, could that be wrong once again because of the way the algorithm works? Could this be considered as an error? Perhaps, but in some cases, this actually depends on the context of the problem that we're trying to solve. For example, the very fact that we're getting a sample which is also a bit further from the other setosa flowers that we see here, kind of on its own down there, the fact that this sample has now been grouped along with these other samples right there, even though it's actually pretty far from these as well, could actually indicate that there is some reason why this is differentiated. Again, in the context of Iris, this is more likely due to the way these algorithms work, but I'm trying to extend the insights or the conclusions that we might run into when using a real-world data set, which is going to be, of course, far more complex than what we have over here with Iris. So again, we can see, and the same case can be pretty much be made for pretty much what we've seen before with the versicolor and virginica samples. As you see right there, we basically have the same kind of thing going on here. So we have these samples again being assigned to cluster 0, and then we have some other samples there belonging to either cluster 0 or 2. So this is another type of differentiation, because if you can basically see here, these points have been considered to be part of the same cluster before using k-means, whereas here they were actually supposed to be parts of different clusters. So the main thing here, just to make things 100% crystal clear once again, is that in the case of Iris, this happens mostly because of the way the data are structured and because of the way the algorithms work. Because as you can see, they might be a bit similar, but they have different end philosophies. However, in a real data set where patterns are not as clear, in fact, they are much more chaotic and complicated, even if we're talking about a fairly simple problem, such insights as to which sample belongs to which cluster and ground truth, if such a ground truth exists, can actually provide deeper meaning or deeper insights to the problem that we're trying to solve, and thus actually enlighten not only us, but also the field experts that we are working with. So having said that, is there any particular question on hierarchical clustering or k-means up until now? Okay. So again, how do we choose k? So the number of clusters that will be created by our algorithm. It's basically the same kind of story as with PCA, or sorry, with k-means. So again, you would either have to empirically select a specific value for clusters, and this can be a bit exhaustive to do, or you could use some kind of an optimization algorithm. Or if you actually have a ground truth that is available, through your data set, right? You could actually try to implement this or take advantage of that in order to at least use it as a starting point. But this doesn't mean that you will always have to use this as the basis, as the concrete basis for your final results. For example, just because we have 3 categories right there with Iris doesn't mean that we would always have to use the same number for k. For example, we could also check out what will go on if k equals 4, for instance. So let's check this out as well. So things change a bit further compared to what we had, right? So the same thing basically applies as we've seen before with k equals 3. So again, this green point differentiates itself from the rest of the setosas, and it basically goes along with the versicolor flowers that we have. But we now have a fourth team right there, a fourth cluster of these Virginica flowers that are actually even further differentiated from the other ones that we have in group 3 and 2. So the reason why I'm doing this, like the reason why I've changed the number of clusters to 4, is that so that we can actually understand that in a lot of cases, even if you have a predetermined set of values for our ground truth, playing around with various different values for k, and in some cases larger than what you have for your ground truth, might be beneficial for understanding which samples could further differentiate from the ground truth itself. For example, as part of an insight, from my own experience in the world of biomedical informatics, there was a time back then when we actually made a hierarchical clustering of patients which actually had prostate cancer. And there were 2 types of prostate cancer that we were checking. And there was a pattern very similar to this, right? So we had basically patients that tried to differentiate themselves from the rest within a particular group like that. And when we used k equals 4, like in hierarchical clustering, because this is the exact same algorithm that we use here, we saw a pattern like this. Like there is a distinct group that does not belong really into either 2 of the values that we have for our ground truths. And this was a point of thinking for the biologists and the doctors that we had in the project. And what happened is that they found out that these samples differentiate themselves because there was also a third subtype of cancer that was actually more aggressive compared to the other two. So the reason why I'm putting this into a bit of a context is so that we can actually understand that just because we get different results doesn't mean that it's wrong or it doesn't have any meaning for our final interpretations. It could actually provide new insights to the project and the problem that we're trying to solve and make research on. So are there any questions for this? I'm switching back to the chat to check if anyone has written something. So okay, so the final algorithm that we have is DBSCAN. It's density-based clustering. So the difference is that this is actually the most complex of the clustering algorithms that we have. And the first difference between this and something like k-means or hierarchical clustering is that this one does not have a k-parameter. So you cannot really set the number of clusters that you want this algorithm to create, which can be kind of a double-edged sword. So in one side, it can be an advantage because you will not run into additional bias for your analysis since you don't really have to make that choice yourself. On the other hand, however, in some cases, it can create an excessive amount of clusters or too few clusters, according to, again, in relation to the problem that we run ourselves into. So the way this algorithm works in a very high level manner is that it actually takes account for the spatial coordinates of our data. So basically what it tries to do is find out in our feature space which samples are very, very, very close to each other. So it tries to highlight specific areas that are dense or densely populated with sample points. And you can see that this algorithm actually works very, very well if we have nonlinear, weird, complex patterns such as this, smiley face right there, which is, it's kind of a funny, ridiculous example, but it's made so that we can actually understand where such an algorithm would shine. So how would we go on to use DBSCAN for iris? We would actually, again, initialize it as such, and then we would basically fit predict on our model. And then we would get the result, the final result. So as you can see right here, this is actually quite interesting because it basically shows us that DBSCAN did not really do anything, right? It did not really provide any insight to our data. So why is that? So the reason behind this is because DBSCAN has been made from scratch to be able to discern very complex nonlinear patterns when it comes to very close, sample points within our data. And what that essentially means for us is that in a lot of cases, especially when it comes to data that might be complex but still have linear patterns within them, DBSCAN might not really do all that great of a work when it comes to distinguishing between different clusters. And this is pretty much why we get a result such as this, where everything has been placed within the same group, within the same cluster. So just as a key takeaway from all of this, which algorithm should we use? Which clustering algorithm should we use? I would say that it depends on the context and the problem and the data set that we use. And we're going to make things a bit more concrete in a teeny tiny bit. So we're also going to check a different data set to get a better understanding of what I mean by that. So how do we also go on to evaluate, such clustering algorithms? Is there any way to basically be able to make an amount of the clustering effort that its algorithm did? And the answer to that is yes. We basically have evaluation scores such as silhouette. So the silhouette score is perhaps the most well-established metric when it comes to evaluating clustering. It has values that range between minus and +1. And the meaning that these values have are the following. So if you get a value very close to -1, as you can see here, the data points in terms of clustering are chaotic, which means that clusters are all over the place. They do not really have any meaning for what we want to do, and thus you should go on and use something different. If you have a score which is 0 or very close to 0, then this is an indication that you do have, some clusters, some groups of data points, but these are not 100% clear with each other. Like there might be overlaps between clusters. So although there might be some kind of a discerning pattern, it's not all that clear. And a value that is very close to 1 indicates that we have very clean, very precise, very concise clusters that are actually pretty far apart from each other. So it basically means that we've achieved the optimal clustering in relation, of course, to the data that we're using for our project. So how can we actually use this metric in order to evaluate the results that we got for these three algorithms, of course? Well, by basically using silhouette score, which is a function provided by scikit-learn, and also evaluating the labels that we have with the clusters that have been created. So as you can probably see, the best algorithm that we have is k-means. It has the highest of scores. Still, the final result, we would say that it's actually quite moderate. And the reason behind this is, of course, because if we move further up, we saw that there are some kind of overlaps, especially between clusters 0 and 2. So it's expected to have a score which is closer to 0, like 0.45. The same concept pretty much applies for agglomerative clustering, because although we have points that are differentiated here, we have a lot of overlaps in this particular part of our samples. And the worst algorithm, of course, the worst one was dbScan, and you can basically understand why. It basically put every single one of our data points into the same cluster. So we would expect to see something far worse than this, but in some cases, these results on themselves can be quite deceiving. So it's best to basically accompany them with some kind of visualization, like a 2D plot, like a PCA, or perhaps a TSNE or a UMAP if you're dealing with a very complex data set. So are there any questions up until this point when it comes to using these algorithms and perhaps evaluating them using Silhouette? Is everything clear up until now?
Yes.
Okay, so here's the thing. We're going to make a short break so that we can drink a bit of water, get a few breaths, and we'll be back in 7:30. So in the meantime, I'm available to use for questions or anything you might want to discuss on the concepts that we're discussing. So 10-minute break. Okay, so can you hear me?
Yes.
Okay, great. So we're back again to conclude today's lecture. So far we've actually seen what goes on in terms of clustering in a simple, data set in the form of iris, of course. So what would actually happen if we tried to, I'm also guessing that you can see my screen, right? So just a confirmation before I move on would be fantastic.
Yes.
Okay, great. So as I've said, we've seen what goes on with Iris, which is a fairly simple data set which has, linear patterns within it. So what would actually happen if we tried to employ the same algorithms in a complex data set, like a nonlinear data set, something like this thing, for example? So this is exactly what we're going to try out now. So we're going to check out the noisy circles dataset. So this particular dataset, as a reminder, is also within this clustering data folder. It's this noisy circles DF, and it's also part of the zip file that I've sent you over through Mega on the chat. So you are going to have access to it should you want to check it out for yourselves, or if you want to check out some other additional, clustering benchmark data sets so that you can actually play around with the algorithms that we're seeing today. So the first thing that we gotta do, again, is basically load our data. And how do we do this? We basically use this particular function from pandas, which is read CSV. So we're not loading any native data set. We're now reading from our computer's disk. And as you can see, this is the data set. It has an X and a Y. And if we try to visualize it, we're going to get something like this. So in this particular case, how many clusters would we actually say that we have? Like, if we had to guess, since there is no ground truth, how many clusters would you say that this data set includes? Like 3, 4, 2, maybe 1? Like, what would be your opinion on this? Would anyone like to try out?
2 clusters.
I also
Like
say
yeah, those are like circular data sets. So
Exactly. So essentially, the reason why we have 2 clusters, just to make things clear for everyone, we basically have this large ring, which would serve as our first as cluster number 1, for example, and then we have this smaller one, which could serve as cluster, number 2. So what would actually happen if we try to run the algorithms that we have on this data set, right? So let's check what would happen with k-means. So we've said that we would expect to have 2 clusters just by looking at the data set. So let's check out what would happen with a k of 2, right? So again, we run the clustering that we want to do. And then, of course, we're using the plot clusters function, which we have as a homemade function right up to here. So wait, so this one right there. So again, I'm showing you this to highlight the power of Python because I've made this function with multiple lines of code once. And when I want to go out and use it, I can simply call it like so in a 1-line, piece of code. So when I try to visualize the results that I'm getting out of k-means, what we're actually seeing here is that unfortunately it has created 2 clusters, but it's not in the correct order which we would actually expect. So it basically says for k-means, the 2 clusters are the 2 different like hemispheres, so to speak. Like this one along with this part right there, and the parts at the top form their own, cluster. So this is an indication right there because this is a benchmark. This is a real benchmark data set, by the way. So this is an indication that for such nonlinear patterns, k-means does not really do all that great of a job. So let's move on to something different. So what if we run agglomerative hierarchical clustering for our data, right? So if we try to do the same thing, we're going to get pretty much the same kind of result. Some data points here and there might be a bit different in terms of the group that they belong to, but the pattern is pretty much the same, right? We basically have two distinct clusters that are determined by the different hemispheres of data that we have. So again, this is due to the nature of how agglomerative clustering actually works. It's a fairly simple algorithm, which means that it's computationally inexpensive and quite fast to run. But the problem is that when you run into such data with complex nonlinear patterns, again, it might fail to actually find out which are the true clusters. So we just keep this in mind for other data sets where we don't really understand or know what will go on from in the first place, basically. So what would actually happen if we use dbScan, right? So if we go ahead and use dbScan, you can see that dbScan actually did exactly what we wanted it to do. So it managed to create two distinct clusters, and it also managed to understand that this external ring is its own cluster compared to cluster one, which is this internal ring right there. So the reason why I'm showcasing this is because back here we saw that dbScan did a horrendous job on Iris, which is a fairly simple data set with some linear patterns within it. However, dbScan, the same exact algorithm, actually performed really well. It actually managed to outshine, hierarchical clustering and k-means on this complex nonlinear data set. So just as a final conclusion to all of this, and I want to show you this picture right there, which clustering algorithm should we be using? So I think that it's clear, by now that it all depends on the context of the problem that we're trying to solve, once again, and on the data set that we have at hand. So if we actually visualize our data set with either PCA, UMAP, TSNE, or what other method of dimensionality reduction you choose to use, and we see very complex, nonlinear, cylindrical patterns almost, then it would probably, with also dense neighborhoods, it would actually be a better idea to go for something like dbScan or other similar algorithms to it, like HDBScan or, for example, optics. All of these are dense-based clustering methods that are pretty much optimized to run with, not a lot of computing power, essentially. If we have a data set which is linear or has simple linear patterns, then it might be better to use something different. It might have been better, for example, for something like this, as you see right there, to use k-means, or for example, hierarchical clustering, pretty much as what we've seen with the example over at Iris. And the same thing can be said here for data sets such as this, like where we would expect to have some sort of line which would actually differentiate between samples, but it's not really all that clear because the data points that we have are very, very close to each other. You could start with something like k-means and then go out and try one of the more complex algorithms that you have. And the reason why I'm showing you this is because, being able to execute these kinds of algorithms and then visualizing results is fairly easy. As you can see, it's only a few lines of code, and it's become even easier nowadays if you use a large language model like ChatGPT or Claude or whatever. But what's actually hard to do is understand why we're using such algorithms and what are their use cases. In other words, right now we live in an era where we have a lot of different tools and of course a lot of different variations of such tools. But the hard thing is, the challenge for us is basically to be able to understand when we should be using these tools and why we're actually using them. So with that being said, is there any question for what we've seen today when it comes to this data set, or perhaps some other things that we've seen in the start of this lecture? Okay, so that was pretty much it for today. We actually finished a bit earlier compared to yesterday and the day before yesterday, but I don't really want to spoil classification. We are going to focus on that tomorrow. So if there's nothing, if there are no questions or whatever, the materials for today's course have been shared upwards. You can basically move into the chat and gain access to them. So thank you very much for your attention, and I will see you tomorrow. And of course, you can always feel free to send me a message either here on Teams or through an email if there's anything you would like to discuss. So um, thank you very much. Have a
Thank
good
you.
one. Okay, so good evening.
Thank you. Goodbye.